I have a spooky clock that chimes and moans when it turns on the hour. I didn't consider how that might be a little embarrassing. It's in my closet. I'm in my closet so the dogs don't yell at me. Red's been vocal today. Hey. Angela, I emailed you back. I don't know if you got my email. Or was it Lindsay that emailed me? It wasn't Lindsay. Hopefully she told you that I emailed you back. Yeah. You can find SP pretty much everywhere. Hi, Red. Yeah, the SP3 and the SP2 are pretty easy to predict because they kind of fall right at that 80 mark, but SP can kind of be anywhere along that line. I am in my closet. My Red is a very vocal dog. He gets really nasty and starts fussing at me, and he's been doing it all day, but he doesn't usually do it when I'm in my closet. So that's why I'm in my closet. You also notice there's a kitty gate in my closet to keep my dogs from rubbing up against my dresses because they come in here and they start rubbing on everything. They're kind of crazy. What do you guys want to work on? Angela and Brandy. It actually tells me there's 6 of you watching, so. And yes, I'm a Southern woman who drinks out of mason jars when I'm at home. It's because I just ate pretzels. Well, fine. Melissa, have we ever practiced that in class? Nope. That's really challenging to do. And pretty much nobody uses it for that anymore. Unless they're doing kind of high-end, I don't want to say that. There are some chemical biologists I know that do it for biomolecules, but we're not going to be doing that. Alright, so here is formula. Sorry, I can't do smooth. It will not. Okay. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. I can't do superscripts and subscripts. But here we go. Oh, wait. Why would we divide a molecular weight by 2 for a potential peak in mass spec? Because it's mass over charge. If you have a charge of +2, you got to divide it by 2. If you have a charge of +3, you got to divide it by 3. If you have a charge +1, you divide it by 1, you get the same number as what you started with. Yes, Lauren, I'm in my closet so the dogs won't bark at me. This is not the first time I've had to do this in my closet. If you look through my old videos. Just depends on how Red's acting. Oh, why it's called de-shielding on NMR when really isn't the electronegative atom shielding the hydrogens? No. It's de-shielding them because it's pulling the electrons away. NMR measures protons, right? It's measuring the nucleus. So if you take the electrons away, it's de-shielding the nucleus. Hi, Duncan. Hi, Heath. Hi, Lauren. Hi, Lindsay. My gosh, the entire class is here. Melissa, let me know if that makes sense. What the heck? I already answered that. Duncan. Stealing my thunder, coming in late. I don't need to do these things if you guys are just going to teach each other. That's fantastic. And yes, for Lauren, Duncan, Heath, and Lindsay, and yes, I'm in my closet. It keeps the dogs from barking at me. Any of you who have huskies would understand. I am taking questions right now. Duncan, what do you think I'm doing? I'm not here for my health. I just gave you guys a problem if you wanted to practice one. The formula is C4H9Br. I wrote it up at the top. In the, right there. Can I like highlight that? Okay, yeah. There's the formula if you guys want to work on that. Lindsay, what would be a potential IR question that I could ask? Something like, if you did this reaction, how could you tell if it worked? I'd give you a reaction and you could tell me if it worked by using IR and explaining how. And you will get a shift or a table of the wave numbers for IR. So you will have those ready and available. It's basically the same thing we've been doing in lab. I know you've missed a few labs because you've been kicking soccer balls, but this means kicking soccer balls. I don't know. So, you know, if you did a reaction that was like a reduction of an aldehyde down to a primary alcohol or something, you know, the shift for an aldehyde is going to be different, or I keep saying shift because we're doing NMR. Lauren, I can't zoom in for the number of peaks, but I can tell you it's a doublet, a multiplet, and another doublet. I'm using a different website for this, so. Duncan, look at the look at the axis and tell me if that's carbon or hydrogen. 1-bromobutane. Yeah, it's actually I think it's a C4H9 3. I think it's a septet 7. Exactly, Duncan. That's how you can tell if you're looking at hydrogen or carbon. The scales are way different. Formula C4H9Br. And then, oh, I can use this here. Can I, let's see. Yeah, okay. You guys can see my cursor, hopefully. So this here is a doublet. This here is a pretty big multiplet. And that right there is a doublet. That one is, let's see. So the doublet that's really far downfield or upfield around 1 is 6 hydrogens. Let me just type this up for you. That'll be easier. I brought all these spectra up, but I think this will be easier. So, tools. All right. So at about 1.0, we have a doublet that is worth, its integration is 6 hydrogens. And at 2.0-ish, we have a 6, 7, 8. It is a 3, 4, 5, 6, 7, 8. I'm just going to call that a multiplet because it would be complex splitting. And that's 1 hydrogen, that's why it's kind of tiny. And then you have at about 3.3-ish a doublet that's worth 2 hydrogens. So sorry, I can't show both screens at the same time the way I have it set up right now. Oh, and I need to scroll back down, sorry. Good job, Sean. 2-methyl-1-bromopropane. Let's draw that sucker out. Wow. Ah! I hit the wrong thing, sorry. Propane. 2-methyl. 1-bromo. Something like that. So the doublet worth 6 hydrogens. We'll call these hydrogens A. That would correspond there. The multiplet with 1 hydrogen would be this one here. Wow, that's a really bad B. And then that there would be your carbon, and you would expect, or your C, you would expect that to be downshielded, or downfield a little bit because it's deshielded by the bromine. Nice job. You guys want another problem? Sorry, before I got in here, I just downed a ton of pretzels, and now my mouth's all like salty. You guys want another problem? All right. Duncan and Lindsay, did you guys get that one right? pulled up like a billion of these in my computer. There we go. So here's mass spec with 1,2-ethane diol, also known as glycerol. Sean, it would have been a, let's see, one hydrogen, so it'd be a triplet of septets, and they'd probably be on top. It would be nasty. You can just write multiplet. Yeah. Yeah, you got it, Duncan. All right, so 1,2-ethane diol. Good thing to start here would be the structure. So figure out the structure. Should be pretty easy. And then we'll want to pick out a couple things. So let's pick out, let me write this down. Write down the formula, the molecular weight, structure. If you have the structure, I guess you don't need the formula. You can figure that out. My dogs are so special. So let's see, the formula, molecular weight, the structure. Find the M+ peak, so the molecular ion peak. That one actually doesn't have an M+1 because the base peak is not the molecular ion peak in that case. So I also want you to find the base peak and find at least one fragment ion. Okay. So that's a pretty representative mass spec problem. If you can answer the questions that I just put out, and if you could find an M+1 peak, even though there isn't one in this case, but if you could find an M+1 peak, then you're good. You are hitting all the milestones I expect you to have for mass spectrometry. Also, I would expect you to be able to look at that spectrum and tell me that it's a hard ionization because it's been fragmented into lots of pieces. But you guys seemed to know that really well the other day. So. I think I can use the snipping tool on this. Let's see. Oh, awesome! That is fantastic. Check this out, guys. I am able to use the snipping tool put that in paint so we can draw on top of it. That's useful. You do not need a calculator to count whole numbers of carbon, oxygens, and hydrogens. I expect you can do that. None of our problems are going to be big enough. You're going to need it, I assure you. I mean, I'm going to be honest here. If you guys can't add up numbers, I don't think you should be passing the class. Not trying to be nasty, but you should be able to add up whole numbers pretty quickly. Oh, hey, I think there actually is an M+ on there. Can you guys see it? We're under pressure. Well, did you just solve it? Duncan got it. All right. So let's see here. Oh, wait. I wonder if I can do... All right, I'll just do a brush then. And pick something that's not red. I feel like we can see teal pretty good. Okay, so... Yeah, Angela, you might have messed up your name because you used to sleep 2 hours a night. I have faith you can do it this time. All right. So this was ethane 1,2-diol. Whoa. Went too far. All right. So what's our formula here? C2 H246 O2. I'm going to scoot this down just a second. So 2 oxygens weigh 32, 2 carbons weigh 24, 6 hydrogens weigh 6, so 10, 11, 12, 62 grams per mole, or you could use AMUs in the context of mass spec. So if you got 62, you're doing good. So it looks like right there, that big peak there would be our M+ peak. It looks like there is a really, really tiny M+1. Really, really tiny there. It's like a little nib. This one here scaled to 100, 31 is the base peak, meaning it's the one scaled to 100. That's all that word means. And let's see, what else did Duncan get here? There are OHs on different carbons, and the 31 peak is with the carbon-carbon bond split making CH2OH. Would that give us 31? Let's see, 12, 16, 26, 27, 28, 29, 30, 31. I agree with that. Cool. Yeah. So if we... let me change that color. If we split along there, that would give us CH2OH units. And I didn't make a second fragment peak. Oh, Duncan, that's okay. I mean, like, you figured out what the base peak was. I'll count that for this. Because you did determine what a fragment ion was, and that is a fragment ion, so I'm good with that. The base peak is the largest peak. That's correct. Lauren, Mackenzie, could a fragment ion be at 31 since it's half the molecular weight? Yeah, you know, that's actually true too. The reason why we might have one at 31 is because you might have the structure with a 2+ on it. So that 31 could actually be that as well. So there could be two things making up that 31 M over Z, right? Mackenzie, you'd have gotten full credit for that. Duncan, you would have gotten full credit for that. Duncan, what are you asking me? M+2 question mark? Does that mean you don't understand what M+2 is? Would the 32 be the M+1 peak for the... Yeah, I think so, Heath. Okay, good. So yeah, if you were looking and you're like, well, what's an M+1 peak? Well, that little tiny one over there I talked about was an M+1. That 32 right there could be an M+1 of the 31, right? So if you had the unit here and it, you know, you cut it in half and then had a +2 charge on that, that could give that right there. Is it possible to knock off an OH? What is 62 minus 16? So 62 minus 20 is 42, 43. Is that 46? Is there anything at 46? No? Maybe I counted that up wrong. What about 29? 17. looking to see if there's any others. Did anybody get any other fragmentations? Well, I am doing it all in my head, Angela. Don't be nasty. Okay, 62 and 17 is 45. Is there anything? There is a little tiny nib at 45. I think whatever 43 is interesting. So a peak with a 2+ charge is, you would have M over 2. In my head, you can see this. I don't know if you can. Please don't fail me. I haven't failed you yet, Angela. Yeah. Okay, so yeah, if we pop off a hydroxyl group and we get 45, if you wrote down that that 45 could be from that, that's fine too. So Lauren and Heath, if you guys found those and you're like, I think that could be that, I'd say, that's a reasonable guess. And then, what is a 29? What do you guys think 29 is? Let's see, that would be 16, 26, 27, 28, 29. I wonder if the... So because these have the OHs on there, you can get that alpha cleavage, right? We didn't talk much of the detail about that, but that's a possibility too. All right, cool. Well, I think you guys got this one pretty well. You got what I expected out of that. If you notice, I didn't have, I accidentally, when I did the cropping, I cut off the axis label there. So that would be relative intensity. So it's basically a percentage, where the most popular one, I guess, popular being, you know, that's going to be the most. Yeah, I mean, that's what I was thinking, Duncan, but I don't know. I don't know where that hydrogen went. Oh, anyway. So that's a good example of like a representative mass spec problem, meaning I want you to know where the M+ peak is. I would like it if you could pick out an M+1. I would like you to be able to pick out a fragment peak if you have a hard ionization. I want you to be able to tell if something is a hard ionization or soft ionization method by looking at the spectrum. And I think that's about it. And yes, I do expect you to be able to come up with a molecular weight pretty quickly. The exam itself isn't too long. I put on a page of like short answer type questions, and there's 2 NMR problems and an IR, couple IR questions. I think that's a total of 10 points for IR. And then the mass spec questions, that's 15 points. So that kind of gives you some breakdown. The NMR problems, the 2 that I gave you, have the carbon and the proton NMR. So it's very similar to the kind I had last year. Yes, Lauren, because last year that's what I covered. And Heath, no. I've repeatedly said in class you do not need to know the mechanism for the McLafferty rearrangement. You guys never listen to me. Yeah, I don't know. Sure. See if I can find one. Do this thing. Copy. paste. Okay. So let me make sure this is showing up for you guys correctly. Oh, you guys are ridiculous. Okay, let's see. Melissa, I'm not giving any examples of those because there's several in your book and you can look them up, and I'm not asking you any questions on them. So if you want to know more about them, look them up, and if you have questions about that, then you can come see me. I'm not going to spend time going over it tonight. Okay. All right. So here, let's say we were doing some sort of reaction, because that's what chemists do, right? And we went from, that's really bad bonding. Ah! Too far, too far. All right. Oh, goodness. There we go. So let's say we go from propine, make space. You guys make me feel like I'm being so mean. All right. So let's say this is what we were trying to do. We've learned this reaction before. It's a hydration of an alkyne. So I'm just going to put on plus water because there's a couple different ways to do that, and I don't care which one we're using for this. So, no, Lindsay, you don't need to know all those. Okay, so let's say we're doing this type of reaction, and we want to know if we got our product. How could you tell? You'll have a table of the wave numbers for different functional groups. So if you go and look one of those up right now on your Dr. Google, you should be able to tell me. What type of oxygen, Lauren? That is the one that you're using. That's the one that I have literally copied and pasted from the internet and plopped it into your exam. It also means the exam's 5 pages because I had to make structures big enough for you guys to see them and everything. So if you look at it and you're like, this feels like it's more of a packet than I'm used to, it's because there's only like one problem on a page. So yeah, absolutely. Okay, so Lauren, you're close. Carboxylic would be like a carboxylic acid. So if it's just talking about a carbonyl, C double bond O, we just call it a carbonyl. A carbonyl could be a ketone, a carboxylic acid, an aldehyde, an amide. There's a couple, an anhydride, some of the functional groups we haven't covered yet. So, but yes, you're correct. So if you were like, yes, that did work because there's a carbonyl at 1710. And if you look, right there, that guy right there, 1650 to 1780, and you see that it's strong, the intensity is strong. That 1710 is pretty strong, meaning it has a really, really high absorbance, I guess, low transmittance. So it goes down really, really far compared to the other ones, the other peaks. Does that make sense? Does everybody now know what I expect you to be able to do with an IR? Because that's it. If you have more questions on what you expect out of an IR, please refer back to this problem. This is very representative. I could ask you what an axis is, like what axis, you would have on IR. I expect you to kind of know, like mass specs M over Z. What is M over Z? NMR, you have the little delta sign or ppms. So yeah, that kind of thing. C double bondo. It's like one of the few things you can do on the computer. Oh, okay, Heath. Gosh, you guys are so weird. Let me see, what do you have up on your screen right now? All right, let me take this one off. No, Duncan, I'm not pulling that up because that would require me to do a lot of stuff on my computer right now. And I already have about 18 windows open. So, sorry. All right, let me do this. All right. Heath, you wanted a hard one. Maybe this isn't hard for you, I don't know. Can I scoot? Oh. Okay. I'm gonna make it go away for a second. The website I went to has, like, it's just a repository for spectra. And so it has, like, if I scroll up a little too far, it has the name. And if I scroll down a little too far, it has the structure. So I'm trying not to give you the answer. Okay. So let's say I have something like this guy. And I'll tell you the formula. I know. Give me a second, Angela. I told you guys I'm working with like 1,000 screens open right now. Okay, so this is, let's see, C5H, 1, 2, 3, 4, 5, 6, 7, 8. Okay. C5H10O. And am I looking at carbon or am I looking at proton? NMR. Thank you, Melissa. That is correct. You can tell because proton NMR doesn't go from 0 to 200 and something, right? You know this. I'm really comfortable with what you guys know right now. Like I'm really confident for your exam tomorrow. I'm feeling really good about it. So don't prove me wrong. But you guys have been doing really, really good on questions in class. And the ones on the exam aren't really like ambiguous where you would need a table, pick up a whole table of data to, or table of chemical shifts to be able to figure out what things are. So, because you know, sometimes it could be in between. I'm going to do that snipping thing where I can pull this up. Did I lose connection? I can see you. Did I go away? Can you see me? I'm here. Okay. Yeah, streaming weird things happen sometimes. Okay, great. All right, so this is a carbon NMR. And for those of you who are like, there's got to be some sort of carbonyl in there, I agree with you, because you can see that, let me pull this up, make sure I'm, okay. So if you were looking at this and saying, I think that this thing here, whoops, there we go. If you're thinking that's a carbonyl, C double bond O, anytime you're like in this general area right here, right, that's where I need you to think about carbonyls, okay? They're real easy to see and pick out, just like you expect. Like benzene is really easy to see in proton NMR. Carbonyls are really easy to see in carbon NMR, carbonyls, okay? So as long as you see something down there, think carbonyl. It doesn't tell you if it's an aldehyde, a ketone, or anything like that, but that's okay. So there's only 3 peaks here, but there's 5 carbons, right? So there's only 3 equivalent ones, right? So if I pop that on there, my formula C5H10O, that's 1 unit of unsaturation, right? So 1 unit of unsaturation means there has to be 1 double bond. And the other 2 carbons that I have, I'll number them 1 and 2, those are going to be in the sp3 region. Couldn't be sp because I don't have any other units of unsaturation. So if I only have 2 other carbon types, but I have 4 other carbons, that means it's got to be 2 and 2, right? They've got to have some sort of symmetry. So if you are thinking something like this, what would the name of this be? Because, you know, we're chemists. We know nomenclature. We have words to use to describe these things. Now that one was hard because Heath asked for something a little harder. I consider this one a little bit harder because you're used to using a lot of protons and being able to rely on those. And in this case, there wasn't a proton. There was only a carbon. Okay, you had the formula and you knew the carbon, and it was pretty obvious, I thought, that there would be a carbonyl there. So, any comments on that? It would be 3-pentanone. Yeah, pentan 3-one. Something like that. Heath, did you get it? Mr. Montana? Need more of my mason jar water. I'm feeling confident for you guys too. I mean, it's always good to work problems, right? I think it's important that we get together, even if it's remotely like this. I know a lot of professors don't do it, but I do think it's really important just to kind of gain that confidence after you've had all that time to study. And I'm sorry that, you know, I had to delay this. Hopefully everybody got the email I sent out, and I posted it on the class Facebook page as well. I did end up getting stuck in traffic for a half hour, but it wasn't in Nashville. It was right before exit 11 where I need to get off to come home. So they were doing construction and I was delayed for a half hour. So it's a good thing, because otherwise you'd have been sitting there waiting for me. You want to do another one? Oh, Lauren, thanks for asking. Yeah, so she's just elderly. She's got a case of the old. She's like 12 or 13-ish. I mean, I got her at the secondhand dog store, so I don't really know how old she is. She was an adult when I got her, and she's just got some arthritis in her back legs, in her hips, so, and maybe her knees. So she was on meloxicam, but it was causing some kidney problems, it seemed like her appetite and drinking was changing when she was on it, so I put her back on Carprofen. But I have a Costco membership, and drugs are way cheaper at Costco, so I had to go to Nashville to get them. Long story short, let's do another one. Sorry. Let me find another one, because I do have a bunch of these up. All right, we did the mass spec. Okay. There we go. So this one, let me write it down for you. So this one has a formula of C7H8. So look at that. Think of your units of unsaturation, right? Always start with that. I think that's a really important area to start with, since you're going to be able to kind of use that, right? It can kind of help you in guiding you into what you need to be doing. Back over to paint. Pull back up my paint. Oh goodness, that's not the wrong. I'm getting confused. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 10 windows open right now on my computer, so if it's taking me a second to click back and forth, I'm sorry. All right. So let me make sure you guys are seeing what I'm seeing. All right, looks good. So let's work out, let me give you some information on this. So C, I don't know if it'll let me do subscripts in here. Hey, it does, look at that. Lets me use shorthand. C7, H, 8. Nice. So let me pull up my brush. I'll do green. So this one is a really big multiplet. Okay. This one here is a singlet. The integration for these is 5 hydrogens, and the integration for this is 3 hydrogens. So with that knowledge in mind, let's start thinking about things. Oh, Sean, you did it too fast. Yeah, you're right. Was that one really easy? Cyclohexane with a methyl would have way more hydrogens than 5. What you should be seeing, like this should be kind of automatic, is you should look at that and say benzene. Okay, because yeah, a benzene ring with a methyl, toluene. That's the name for it. So you should look at that and automatically think benzene, because it's worth 5 hydrogens and it's down in the 7 region. Okay, like 7-ish, like that area there is benzene. Okay, so aromatic hydrogens. And then because there's 5 of them, that means there can only be one thing stuck on it, right? If there were only 4 hydrogens, it would mean 2 things were stuck on it. Okay, So you have to think about that. And then the other thing I have is a CH3, and it's a singlet, meaning it's not being split by anything. There you go. I feel like that one was too easy. Sean got it in like 2 seconds. Some of these, though, it's like once you see them, like it can be immediate, but if you don't see it right away, it can take you a few minutes. So you have to like work through it, but I think you guys did good. Okay, well, let's do another one. I have a few more minutes. Do you guys have a few more minutes? Let's see, we did that one already. Okay, maybe this one, you won't get it immediately. And I'm just going to do this directly on here instead of switching back windows. Okay, back to here. Okay. So this one, a little bit harder maybe. So this would be, oh, I'm in purple mode, so C8, H, H10. Okay. And so let's pick out what we've got here. This here is a singlet. Worth 6 hydrogens. This here is a multiplet worth 4 hydrogens. It's got complex splitting. Ah, you're close, Duncan. Close, but not quite. So, if I can, no, I can't do that. Okay. If you have it in the 1 and 4 position, like let's look at some options here. So I think that everyone should be able to see that this here is a benzene ring, right? And if it has 4 hydrogens on it, that means there's 2 substitutions. So that means, and I'll show you guys some weird little notation for this. There's 2 CH3s on it, and when I'm drawing it that way, it means we don't know where they are yet. So it's like just a wiggly little line in the middle of the benzene ring. So the other day in class, and this one was kind of hard, like I wouldn't, Heath asked for more hard. So this one, you have to kind of think about the different options, okay? So that's an option, and I'm just going to leave those bonds open because they mean methyl anyway. Okay, those would be our 3 options, correct? Angela is saying this one. Duncan is saying that one. Melissa said that's what I had too. I don't know if she was agreeing with Angela or Duncan. Y'all are all really close. It's actually this one here. And so you might say, how do I know that, right? Well, because I've done this before. But also, if you look at the multiplet that's down there, let's look at the different options for that. So do you agree with me? So this is, that's the Megan one. We had 3 options. I picked the right one, but that's because I know what I'm looking at. So Duncan picked what we would call 1 and 4, or the para position. And if you look, those two carbons and hydrogens are equivalent to each other. Those are equivalent to each other. And these are equivalent to each other because of a lot of symmetry on that molecule, both up and down, left and right, side to side, right? So you would expect to see basically 3 peaks total for those different colors. And so you would get the really big peak down at the at the beginning of the spectrum. And then you would get what would kind of look like 2 little groupings downstream in the benzene region. So I'll just write 7. Okay. For Angela's guess, okay, you would still expect to see that, but this one here is in a much different environment than these 3. Now, I realize the one that I'm coloring in right now is different than the other 2 purple ones, but they're so similar that they're going to be on top of each other. So you'll usually see a grouping like that, where they don't look the same. They're both multiplets, but they're split in 2 different groups, and one will be integrated to 3 hydrogens, and one will be integrated to 1. Okay? And then the one that I have here, in this case, there's also a plane of symmetry. Oh goodness, what have I done? Angela, I think you're right. Oh no, I was right. Okay. I started second guessing myself. But so all 4 of those are going to be, I mean, they're not exactly the same, but they're going to kind of be on top of each other, right? So the ones I'm coloring in are equivalent to each other because the 2 substituents are the same. They're both methyl groups. So those are the same. The other 2 are different, but they're going to end up more like a big messy pile on top of each other. Whereas the other one is a big messy pile and a little messy pile. And then the one Duncan had was like 2 little messy piles. That's kind of the best way I can explain it. But I actually have, let me find it. Browser. Okay, so this one here, there we go. So this is called orthoxylene, if you were curious. And then here is the other form. This was what Angela wanted. Do you see how this spot, it's a bigger mess of stuff and then a littler mess of stuff. And the placement of those could differ depending on what the substituents are on the molecule. And then if things are in the para position, meaning on the opposite sides, because of that symmetry, you would only expect to see, in this case, 2 different peaks, both singlets, because everything would be the same and symmetric. But if you had something else different than methyl groups on both sides, like let's say, let's look up methylphenol. That's my spooky clock. It's the Great Pumpkin, Charlie Brown. And every hour it boos at me. I'll just set it down for now. Okay. So let's see. Oh, there's a good one. So even though this is symmetric, like what you were talking about earlier, Duncan, and you can see you have the 2 kind of symmetric groupings of peaks. This here is the hydrogen peak. Remember I said that alcohols kind of pop up in different places. And then there's the methyl peak down there, very upfield. Okay. Does that kind of make sense? Melissa, they are stacked to similar carbons, but not the exact same carbons. So if you look at, oh, let's see, where are we? What screen do I have up for you guys? Okay. Okay. So let's say that's a chlorine and that's a methyl. Okay. This carbon here in burgundy and the hydrogen attached to it are different than the one in purple, which is different than the one in teal, which is different than the one in bright red. Those 4 hydrogens are all different, as is the hydrogens down here on the methyl group. Okay, so remember, this group here is right next to a CH3. That one is right next to a Cl. This one is 2 carbons away from a Cl and 3 carbons from a CH3. This one here is 2 carbons from a CH3 and 3 carbons from a chlorine. So they're not the same, okay? They're very different. I mean, you can kind of work out those relationships if you want. Now, if you... Oh my gosh, you know what I just found out? I can draw cyclohexane in here real fast. Oh boy, I feel slow for not having thought of that before. Okay. So, okay, let's say I have another benzene. And this time I have a CH3 and an OH, all right? So, obviously that OH is going to be a different hydrogen because it's attached to an oxygen and no other hydrogens are. These 3 hydrogens on the methyl group are all the same because they're all connected to the same carbon, right? If I look at the rest of the molecule, this carbon here and this carbon here are exactly the same. They're both basically 2 bonds away from an oxygen, and they are 3 bonds away from the methyl group. So those are exactly the same, and the hydrogens attached to them are exactly the same. If you look at the, oh, I need a different color. If you look at this one here and this one here, right, those are attached 1 distance away from a carbon with a CH3 and 3 bonds away from an OH. So they are different, right? They look similar, right, but they're not exactly the same. I hope that kind of makes sense. Oh, goodness gracious. Lauren, I just now saw your comment. Why is teal and purple different? I have a feeling you're not talking about the molecule I have up on the screen right now. What did I have on there before? Teal and purple. So, oh, okay. The other example, all 4 hydrogens are off the benzene attached to a carbon with the same things off of it. Yes, and so in those cases, sometimes, like you're talking about with the xylene molecules, I'm guessing. Confirmation, that's what you're talking about? So you're talking about like if I have that. Okay, so if I'm looking at this, so that's a very good question, Melissa. It's just hard to see. How about if I do it this way? If I show you the plane of symmetry that runs down the center of that molecule. Okay? this carbon there is unlike all the other carbons. It's smack dab between two CH3s with nothing on it, right? This carbon and that carbon and the hydrogens attached to that are exactly the same. So if you're looking at those thinking those are the same, you're absolutely correct, right? They're both, right, same distance away from those methyl groups, same distance from each other, same distance from everything, right? They're on either side of that. If you took the benzene and folded it along this line, if it's laying on top of stuff, it's the same thing, right? If it's perfectly symmetric on each side, it's going to be the same thing. Then that last one there is going to be different than the others because it has a different relationship with those other groups coming off and everything else, right? I don't know if that answers your question, but I'm trying. It's hard when we're so far away. I'm sorry. This is best I can do. So the 1,4-dimethyl benzene when I pulled that one up, it had a peak there and a peak there, right? So there was one around 7, and there was one close down there to 0. Put that there so it doesn't look like another line. So it only had one peak. I mean, I can pull it back up if you want. Not the one in the 4. Here, let me show you the... That's the structure in the spectrum. Oh, I think because I was showing you what would happen if you had 2 different substituents on it, so there was no symmetry. So yeah, if you look at this one down here, that's going to be the CH3s. It's actually going to be worth 6 hydrogens because it's both of the methyl groups. And then this one down here is a single peak worth 4 hydrogens, which is why it's roughly 2/3 the size of the other peak. Because there is symmetry in that molecule, they'd all be the same. You could fold it this way and that way, basically, and it would overlap. That's right, Lauren. But so that was the 1 and 4. That is the 1 and 3, where you get that one hydrogen that's stuck between them, which would be that one right there. And then these other 3, they're not equivalent to each other. They're just kind of on top of each other, making a messy multiplet there a little bit upfield, around 7, about 6.9. And then if you look at the ortho, you still see the molecule having 6 hydrogens on a CH3. And then this one you see kind of a mess of stuff on top of each other, because of basically they're overlapping and it's a big messy multiplet. And that's just generally what you see if you see something substituted at the 1 and 2 positions. It can be even messier than that if the 1 and 2 substituents are different than each other. Well, I did pull up like 18 different spectra really fast. Okay, so it's like 10:15. We've been doing this for an hour and 15 minutes. I haven't had dinner yet, so I'm going to go eat some dinner. But if you guys have more questions tonight and you need to email me, that's fine. I'll still be checking my email. Thanks for putting up with me in my closet. The dog's finally shut up and calmed down. Does anybody else have a husky? Do you guys know what I'm talking about? Like, they never shut up. Benzene rings are messy, Lauren. Benzene rings are messy. Hard ionizations blow things apart. Soft ionizations don't. Alcohols end up wherever they want to go. Benzenes are always around 7. And carbonyls are always around 200 on carbon NMR. If you can remember those 6 pieces of information, that'll get you pretty far. Splitting is N+1, right? 2 bonds away, 3 bonds away. I smell my dinner. I'm getting off here now. So, email me if you guys have any questions tonight, okay? Just to reiterate, it is a little bit longer of an exam page-wise because I did put, you know, I tried to make things big enough for you guys in there. There is going to be, you're welcome, Melissa. There will be 2 NMR problems that have both carbon and proton for you to solve. You get the formula for all of them. There's a mass spec problem, 15 points of mass spec problems, 10 points of IR problems, 50 points of NMR problems. So, but I think you're good under that. And then a page of like short answer type things. All right, Duncan, what is your question? You'll be last question. Bye, Angela. You're welcome, Mackenzie. I'm just waiting on Duncan. What's up, Brandy? Yeah, so integrations are messy. We'll see some of those in lab. I'm not going to give you any of those in lecture for an exam because I'm not sadistic. But if you have, like, let's say all of your integrations added up to 4.5. Well, how do you have 4.5 hydrogens, right? That doesn't make any sense. And if you have your formula and you're like, okay, that I actually have 9 hydrogens, so that means you need to multiply all of your integrations by 2 to reach that 9 hydrogen count. And then if you had 18 hydrogens, you'd say, okay, I need to multiply those by 4 to get to 18. So it's easiest if you have the formula, but I always give you the formula because you're pretty much almost always going to have a formula if you're ever doing this. Brandy, were you like giving me a high five, or did you like, was this a raised hand question mark? I'm not really sure. My hair's crazy, but I'm gonna like just keep working with that there. All right, if you guys have more questions, hit me up on an email. I'm gonna go eat a baked potato. I will see you in the morning, my loves. Good night.